Let's go ahead now and take a look at example number 8. This is going to be another instance where we're going to have a limit in an indeterminate power. So notice here what's going to be the case if I have a limit as x goes to infinity of 1 plus 1 over x to the power of x. Now immediately what I can see here is that in the inside of these parentheses, if x is going towards infinity, I'm really going to have 1 plus something approaching 0. And so here I kind of have 1 almost raised to a power. But if x is going to the going towards infinity, then I have 1 to the infinite, and this is one of those indeterminate powers. So we're going to need to take the same sort of approach that we did back on example 7, which is to start with our limit and apply an e to the power of a natural log to make use of the natural log properties and be able to pull that power down. Now I want you to go ahead and see if you can give this a shot here on your own. So go ahead, pause the video, try to work through this to see if you can arrive at a final answer. And then when you're done with your attempt, you can unpause the video to watch me work through the solution. Okay, well hopefully you actually did go through and attempt it. We should have ended up with a final value of e to the first power. So this limit should actually just be equal to the number e. To see how we do that, we can just go ahead and note the following. So I'll say, note that the limit here as x approaches infinity of 1 plus 1 over x raised to the power of x, I could rewrite as e raised to the power of the I forgot my limit here. Could be rewritten as the limit as x approaches infinity of e to the power of the natural log of 1 plus 1 over x to the power of x. Now, I can go ahead and rewrite this again one more time by saying this is going to be e raised to the power of x times the natural log of 1 plus 1 over x. That is, I took that power of x and I pulled it down to the front using natural log properties. Now again, I can have my limit bypass my e and move up into the power. So I'm going to go ahead and say this is now exp of my limit, x moving towards infinity, of x times the natural log of 1 plus 1 over x. Now if I could evaluate this limit, I would be instantly done with this question. But I'll notice here that my x is going to be moving towards infinity, and here I'm going to get natural log of 1 plus 0, or natural log of 1, which is 0. So I have infinity times 0 here, and that's an indeterminate form. But it's not one of the easy indeterminate forms, 0 over 0, or infinity over infinity, that L'Hopital's rule can work with. So I'm going to go ahead and do a little bit of rewriting here. I'm going to re-express this as limit as x approaches infinity of a natural log of 1 plus 1 over x all over 1 over x. Again, doing kind of like an unsimplification. And now I can see that my natural log is still heading towards 0, but my denominator now looks like 1 over x, which is also going to be heading towards 0 if x is moving towards infinity. So it's at this point where I could actually finally pull my first calculus move and make use of L'Hopital's rule. So I'm going to end up here with exp. I have my limit. X goes towards infinity. In the top here, I'm going to have 1 over the inside of my natural log. And then I'm going to have to multiply by the derivative of this input. So the derivative of 1 is 0, and the derivative of 1 over x is going to be negative 1 over x squared. So this is what's just in the top of my fraction. Remember, that's the derivative of my natural log and then the chain rule. So the derivative of the denominator is much simpler. It's just negative 1 over x squared. Now, of course, as I write this, I can see that, wow, I can actually pull a very simple algebra move here and just cancel from the top and the bottom this negative 1 over x squared. And so this is going to leave me with e raised to the power of the limit as x goes towards infinity of 1 over 1 plus 1 over x. Now, again, I could do the limit of the top, which is just 1, and the limit of the bottom, which is going to be 1 plus 0. So this is going to turn into e raised to the power of 1 over 1 plus 0, which of course is just going to be e to the power of 1 which is just the value of e. And so again, what we've been able to see here is that we can kind of take this limit and be able to show it's completely equivalent to the value of e. Now, actually, surprisingly, this is a limit that we talked about near the end of Chapter 3. You could actually go back to that section, I think it was 3.9, and take a look where we actually showed another way why this would be the case. And we kind of have an alternative way here to confirm this. So again, what you'll notice here is that a lot of the movements in this question, a lot of the moves that we make are really algebra moves, right? Like this introduction of e raised to the power of a natural log of something, that's just algebra. Using the natural log properties, that's just algebra. Rewriting this and doing this unsimplification, it's just algebra. Canceling, it's just algebra. There's actually very little calculus going on here. So while these problems may seem intimidating, it might be helpful to just note that it's actually only pulling on material that you have learned in the past, or at least primarily on material that you've learned in the past. And so hopefully you were able to get to an answer here like E, or if not, you were maybe able to see where you went wrong or where you could have maybe done something a little bit better. Of course, if you have questions about this, or if you need to practice these things more, by all means feel free to go through the worksheets, stop by my office hours, and I'd be happy to talk with you about these sorts of questions. The biggest thing before we conclude this section is again to just always remember that in order to use L'Hopital's rule, you have to have one of these indeterminate forms. I really can't stress that enough. So make sure that as you're practicing that you're really careful to note if you have one of these forms. Because if not, you have to go ahead and do big manipulations like we've done here and for the past several videos in order to get to one of these specific forms.